Hello, everyone. My name is Daniel Saavedra, and I hope that you are having a good day right now. The work that I want to present today is called Influence of the Substrate on the Electronic Properties of Graphene Quantum Dots, Confinement, and Quantum Coupling. That's a work made by me, Daniel Saavedra, Carlos Páez, and William Gutierrez Nin. Uh, in this study, we investigate the effect of different substrates on the energy levels of graphene quantum dots. These dots can act as a potential barrier wells, demonstrating confinement effects due to disparity Fermi levels between the materials on the heterojunctions. Additionally, we explored electronic tunneling between two graphene quantum dots by varying both the distance and the relative size between the nanodevices. Our finding revealed the presence of lateral quantum coupling between them, leading to the formation of molecular states. Inspired by the approach used by natural molecules, we propose a classification scheme for these molecular states based on symmetry considerations. Our observations align with existing experimental data, underscoring the potential of this approach for understanding the electronic properties of graphene quantum dots. Well, in the field of experimental research, significant advances have been made in the synthesis of nanostructures known as quantum dots. These nanostructures have the ability to confine charge carriers and exhibit quantum properties by presenting a quantized energy emission spectrum. Graphene, as a material, is a material known for its spatial hardness, flexibility, and high thermal and electronic conductivity, offers fertile ground for research in quantum dot synthesis. Additionally, quantum dots made with graphene offer significant advantage over traditional semiconductors, such as stable fluorescence, low toxicity, and excellent water solubility, make them ideal for a variety of applications in electronic devices, such as semiconductor-based diodes or transistors. Among the most commonly used methods for creating graphene nanostructures is the use of copper through a bottom-up approach. This method involves chemical vapor deposition to synthesize quantum dots on the surface of copper. Another approach involves the use of fullerenes, that is an spherical structure made exclusively of carbon atoms, where a top-down method is used to form quantum dots through controlled chemical oxidation. Recently, the use of CuO, a semiconductor material, has been explored for the synthesis of graphene quantum dots through hydrothermal reactions. In summary, this experimental advance demonstrates that the graphene quantum dots can be synthesized on a variety of materials and substrates, opening a new possibilities for customizing the properties of those nano devices based on their specific application in electronic and other technical areas. Uh, Part of that, there is computational studies that use the tie banding model that can be show the localization of the spectrum of the electron, the distribution long waves. So, so, uh, the objective of the project is to study the localization of the electron wave function in the graphene quantum dots and the influence of the substrate. The model used to conduct this study is the finite element method, which is based on a linear combination of solutions applied at the nodes of the mesh used. In this case, the quantum dot will include the effects of a substrate replicating what occurs experimentally when growing graphene nanodevices. In the graphene region, there will be linear dispersion governed by the Dirac-Hamiltonian, while in the external part corresponding to the substrate region, there will be quadratic dispersion governed by the Schrödinger-Hamiltonian. As a result, the electron will transition from a region with velocities on the order of the speed of light to one with significantly lower velocities. To accurately this model transition, the boundary condition between both sections will be treated as if the quantum dots end with A-type graphene atoms. Thus, the wave function outside the graphene will be represented as a linear combination of the A-type wave functions within the graphene. Well, as the first part of the study, is focused we are focused on examining the effect of different substrates on graphene and how they influence its energy levels. The primary idea was to investigate two different types of potential behaviors, barrier and well, as the figure shows. The three materials used were copper, gallium, and potassium, with the potential barrier formed by the difference in Fermi energies between graphene and the substrates. This study was conducted on a circular graphene quantum dot with a radius of 40 nanometers. The energy spectrum reveals that change in substrate doesn't significantly affect the energy levels, indicating no evident change in energy. Similarly, the densities of states presented below don't reflect a change in the localization of the electron. At energy close to the Fermi level, where the degeneracy of this energy value is shown, the electron is localized at the edge of the quantum dot. However, as the energy increases, the electron begins to localize within the quantum dot. Two bands of higher intensity emerge, which reflect the movement of the wave function and its interference at the Dirac K points, as the figure shown. Second part of the study, uh, the objective of the project was to study the effects of quantum dot geometry considering three different symmetries, circular, triangular, and hexagonal geometries. So, as shown in the previous section, the substrate doesn't have any effect on the localization or values of the wave function. So, we conduct a study using two different models. The first with an infinite potential, representing an isolated quantum dot without any substrate outside of it. And the second one with a potential of 0.2 electron volts. The results reveal significant difference in the energy values of the wave function. Without a substrate surrounding the graphene quantum dot, the three symmetries exhibit relative similar behavior, with the main difference be, being the energy values they present. However, when the substrate is added, the hexagonal symmetry completely breaks the degeneracy that was previously observed, demonstrating that the geometry's influence significantly affects the energy behavior. Regarding the wave function density of states, it's observed that at the Fermi level, the behavior is similar to what was previously shown. The wave function localizes at the edge due to relativist effects, and as the energy increases, the electron begins to localize within the graphene without showing any signs of quantum tunneling due to the electron's high velocity within it. This, as the next step, we studied the lateral coupling between two graphene quantum dots and its effect with an infinite potential at their boundaries, varying the distance between the centers of the two dots. Three distinct distance values were selected to study the effects on the energy spectrum and the localization of the electron wave function in the system. The results show similar behavior in terms of the energy spectrum typical of systems with relativistic velocities. However, it is noticeable that as the distance between the quantum dots increase, the energy values tend to decrease. This occurs because as the area of the quantum dot increase, in this case, the distance between centers, the energy of the system decrease, as reported in the literature before that. Regarding the density of states, at 0 electron volts, the electron tends to localize at the edge of the quantum dots as expected. However, it is observed that at 0.05 electron volts, through quantum dots, the probability density tends to spread between the two quantum dots, something that doesn't happen at zero point 0.1 electron volts. From this point on, the probability density becomes concentrated in a single quantum dot, as we can see in the picture. The conclusion that work have is like the subset doesn't have any substantial effect in the electron localization in the model, nor the energy level showed as an energy spectrum. This is due to the high velocity of the electron in the graphene sun, because it doesn't allow that the electron can pass through the potential barrier. So the electron doesn't feel the effect of any subset and is located just in the graphene sun. We can talk about that the geometry plays a very important role in the energy spectrum of the graphene dots. As we could see, the circle and the triangular shape have a similar spectrum level. However, hexagonal geometry presents less zero states than the other two, and this is related to the graphene symmetry. This is happening without a potential barrier. When we can change the geometry in our model, the hexagonal geometry loses all the zero states degeneracy. It is due to interference effects between the K waves in the K points of the reciprocal zone. We can talk also as a when two when two circular graphene quantum dots are coupled, the energy spectrum shows as degeneracy near to the zero state level, and it can be understood as the electron cannot go with the graphene zone, as the first part of the work showed. So the electron acts as a link between the two graphene quantum dots, what makes possible the lateral quantum coupling. Energy is over zero point 0.1 electron volts. The electron is always located in just one of graphene quantum dots and not in both of them due to the high energy what it needs to chain of sun. So that's the work, and thank you for your attention. Uh, Thank you very much.